Welcome. Today we will discuss reference frame theory. Reference frame theory is essential for advanced machine analysis and for studying concepts like vector control etc. Vector control and other concepts. Reference frame theory is essential. So, we will consider the reference frame transformation from 3 phase to stationary alpha beta and alpha beta to synchronously rotating DQ frame and reverse DQ to alpha beta and alpha beta to 3 phase. All these reference frame transformations we will discuss today. So, the contents of today's talk are introduction to reference frame theory, reference frame transformations, active and reactive powers, power invariance transformation. These things we will discuss today. So, first the development of reference frame theory is like this. In 1929, R. H. Spark introduced synchronously rotating reference frame for stator windings of synchronous machines. This transformation and a transformation is named after him called Sparks transformation, that gives from 2 phase to synchronously rotating reference frame and reverse. So, this is the Sparks transformation given by R. H. Spark in 1929. Then H. C. Stanley gave in 1938 one reference frame that is used as the stator reference frame for rotor windings of induction machine. This is also Stanley reference frame. This is for the stationary reference frame for rotor windings. Then in 1951, G. Krohn gave one introduced generalized synchronous rotating reference frame common for both stator and rotor induction motors. So, that was generalized transformation. So, first we will discuss the 3 phase ABC to stationary reference frame transformations and reverse. So, the stationary reference frame, it is written as normally as alpha beta, or sometime some books, some literature refer it to as DSQS, and 3 phase we are writing at ABC. So, for this transformation, so first we consider the axes. The axes are like this: VAS axis we have taken as horizontal, VBS is lagging 120 degree behind VAS, and VCS, these are the voltages in ABC frames. So, VCS is lagging 240 degree behind VAS, ABC axis. Then we consider V beta S, the stationary reference frame in the voltage in the stationary reference frame beta S. Beta S is at angle theta with VAS, and V alpha axis, alpha S axis is at 90 degree with V beta S axis. So, V alpha beta reference frame is like this. Alpha and beta axis are at 90 degree, and it can be at any angle theta with AX axis. So, now to transform the 3 phase voltages VAS, VBS, VCS into the alpha beta reference frame, alpha S and beta S, what we need to do? We need to resolve the components. For example, first we want to write V beta S. So, V beta S. So, component we consider VAS along component of VAS along V beta S is VAS into cos theta. Then VBS, BS is making angle 120 theta minus 120 with VBS. So, component of VBS is VBS cos theta minus 2 pi by 3, and again VCS will also contribute to VBS according to its component. So, component of VCS along V beta S is VCS cosine of theta plus 2 pi by 3. So, that way we get V beta S by components of 3 phase voltages along beta S axis is given by resolving the components in that axis. Similarly, we can get V alpha S also. So, these transformations are given, transformation matrix is given like this. So, as we have just written V beta S, V beta S, component of V A S along beta S is cos theta, component of V B S along beta S is V S into cos theta minus 120, and V C S component is cos theta plus 120. 120 is 2 pi by 3. Similarly, V alpha S we get component of V A S along V alpha S is sin theta, component of V B S is sin theta minus 120, and component of V C S along alpha S is V C S into sin theta plus 120. So, that way you get V alpha S, and V 0 S, 0 sequence component also can be present. So, 0 sequence component is V 0 S is according to 0 sequence formula 1 by 3 V A S plus V B S plus V C S. 0 sequence component is always like this. So, here to have invariance of the MMF, we multiply a component 2 by 3 with the matrix. So, 2 by 3 is multiplied, so that MMF remains invariant. So, V 0 S, to apply this formula, it is 2 by 3 into 0.5, 0.5, 0.5. So, that is 1 by 3 of V A S, V B S plus V C S. So, this way we get the transformation, that is V beta alpha O is this vector is the transformation matrix K S into V A B C vector. K S is this transformation matrix, and similarly the inverse transformation in the same way we get V A S, V B S and V C S from V beta S, V alpha S and V O S. Along V A S, component of V beta S is V beta S cos theta, then plus V alpha S into sin theta plus V O S. So, you get V S. Similarly, we get V B S and V C S. So, from the second inverse transformation, we get V A B C vector is the inverse transformation is we write as K S inverse and the vector V beta alpha O. So, now we can see this K S transformation into its inverse transformation. K S inverse is the unity matrix, identity matrix of dimension 3 by 3. You can verify that, and that is why you can see that is why the term 2 by 3 is also coming, 2 by 3 term is coming. So, that K S into K S inverse is the unity matrix of dimension 3 by 3. So, now it is very convenient to set theta equals to 0 degree. This is the generalized derivation. It is very convenient to set theta equal to 0 degree. With theta equals to 0 degree, you can see V beta S equals to V A S, because beta axis combines with A axis. So, V beta S equal to V A S, and V alpha S is 1 by root 3 V C S minus V B s, and inverse transformation with theta with theta equal to 0 degree. Inverse transformation is V A s equals to V beta s and V B s is minus half V beta s minus root 3 by 2 V alpha s. V C s is minus half V beta s plus root 3 by 2 V alpha s. So, with theta equal to 0 degree, the transformations are simpler. So, it is very convenient to set theta equal to 0 degree. Then we go to the transformation from stationary alpha beta to synchronous rotating reference frame DQ reference frame. So, as we write alpha for ds and beta for qs, similarly when we write ds qs, synchronous rotating reference frame is also written as DE QE frame, and instead of writing DE QE, we can also write simply DQ. So, VQ and VD are shown at 90 degree to each other, and VQS, VDS are the voltages, and beta and alpha axis, there are beta axis is at theta degree with Q axis. So, that V beta S is making angle theta with VQS, V alpha S is making angle theta with VDS. So, from this transformation, from this reference we can get from beta S and alpha S, we can get VQS and DS by resolving the components. So, VQS is V beta S cos theta e, component of V beta S is cos theta e, and component of V alpha S along VQS is cos theta e plus 90 degree. So, it is minus sin theta e. So, we have plus minus V alpha S into sin theta e, because cos theta e plus pi by 2 is minus sin theta e. Similarly, this is by resolving the components. Similarly, we get V ds component of V beta S along ds is cos 90 minus theta. So, it is sin of theta e, and component of alpha S is plus cos theta e into V alpha S. So, this you get transformation from alpha beta to synchronously rotating DQ, and we can get the reverse also. So, these transformations is known as Park transformation. So, in Park transformation, as I have explained, we get VQS and VDS from V beta S and V alpha S. V beta, so as I have explained, we get these components. DS is V beta S sin theta e plus V alpha S cos theta e. Components, resolving the components we get. Then the inverse Park transformation is from synchronous rotating DQ to stationary alpha beta frame. So, we consider the same reference frame. So, or you get the inverse of this matrix. You have VQS, VDS, this vector is cos theta e, V beta S minus sin theta e V alpha s, and V ds is V beta s sin theta e and V alpha s cos theta e. So, if you take inverse transformation, it will be V beta s V alpha s. It can be obtained by getting the inverse of this transformation or by resolving the components also. Either way it can be done. So, it is V q s V d s. So, inverse of this 2 by 2 matrix is cos theta e along the diagonal, and off diagonals are reverse sign. So, you get these expressions also V beta s and V alpha s from V q s and d s by resolving the components of from of the voltages. So, let us consider the balanced 3 phase voltages. The balanced 3 phase voltages we consider as V A s equal to V m. We consider it to be cosine of omega e t plus phi, because phi is there, we are assuming cos omega e t. So, that V b s is V m cosine of omega e t minus 2 pi by 3 plus phi, and V c s is V m cosine of omega e t minus 4 pi by 3 plus phi. 3 phase voltages are like this. And if we consider now we apply the transformation from ABC to alpha beta, 3 phase to 2 phase alpha beta with theta equal to 0 degree. With theta equal to 0 degree, initial angle theta equal to 0 degree, V beta s equals to V a s. So, we get this equation, V beta s is V a s, that is V m cos omega e t phi, and V alpha s we use that transformation matrix. V alpha s is 1 by root 3 V c s minus V b s. So, if you apply this V c s minus V c s B s 1 by root 3, you get V alpha s as minus V m sin omega e t plus phi. So, now the 3 phase voltages are transformed to 2 phase voltages V alpha and V beta. If we write as a this rotating phasor, rotating phasor, so that is we represent phasor voltage V is V beta s minus j V alpha s, because alpha axis is lagging 90 degree behind the beta axis. So, phasor voltage is V beta s minus j V beta s, V alpha s. So, using that I think V alpha s is obtained here 1 by root 3 V c s minus V c b s is minus V m, like this, minus V m sin of omega e t plus phi, this is what. So, V beta s is V m cos omega e t plus phi, and minus j V alpha s is plus j V m sin of omega e t plus phi. So, this is equal to V m e to the power j omega e t plus phi. So, now this V alpha V beta components combinedly represent a rotating voltage vector or voltage phasor, because this is a whose amplitude is Vm, and it is rotating at a speed omega e t, and at time t equal to 0 its phase angle is phi. So, it is a rotating phasor. What we can write? It has amplitude of Vm and phase angle of omega e t plus phi, and that is the beauty. The 3 phase voltages now transform to 2 phase voltages. 2 phase voltages. So, it is the so instead of having 3 equations, one for VAS, AS, BS, CS, we require 3 equations. Now, number of equations required is 2, because only for V alpha s and V beta s we will have only total 2 equations. So, first number of equations reduces from 3 to 2. So, equations becomes less, so easier to handle. This is first thing. And what is the amplitude of this magnitude of the voltage V? That is V alpha s square plus V beta s square root over. That is, you can find out magnitude is Vm, magnitude. So, this is the transformation from 3 phase voltages, balanced voltages to alpha beta. Now, again we can do the same transformation from alpha beta to DQ, synchronous rotating reference frame, and again for this V beta s as we have written here and V alpha s as we have written here, we apply the transformation, Parkes transformation, which we have just discussed, and we get VQS as Vm cos phi and Vds is minus Vm sin phi. Same thing you can write by substituting these expressions for V beta s and alpha s in Parkes transformation, we get VQS and Vds. So, what we see here, this QS ds is the synchronous rotating reference frame. In the synchronous the 3 phase voltages in the synchronous, when referred to the synchronous rotating reference frame, is represented by 2 components, these are the DC components, because phi is a constant angle. So, VQS, that is Vm cos phi is constant, and Vds, that is minus Vm sin phi is also constant. So, the 2 components are DC voltages. So, 3 phase voltages in the synchronous rotating reference frame are converted to DC voltages, DC quantities. So, that is the advantage of the synchronous rotating reference frame. The 3 phase sinusoidal variables appears as DC quantities. So, it becomes, first advantage is number of equations reduce from 3 to 2. So, number of equations reduced, that is one simplicity. Second thing, instead of sign variation sin omega t cos omega t, we have only DC quantities. So, equations are easier to handle, and also it will be convenient for the vector control, where we require to control the induction motor like DC motor by modeling the induction motor at DC motor and controlling it. So, that is why reference frame theory has a main contribution in the vector control of induction motors, which we will discuss next. So, this is one transformation. There is another set of transformation which is called power invariance transformation. Previous one was the MMF invariance transformation. That means, when we transform from one frame to other, MMF was remaining invariant. Now, another is power remains invariant. So, if the power remains invariant, the transformation is given by like this. So, we have here we represent F. F can be anything. F can be voltage, 3 phase voltages, or currents, or flux linkages, or simply flux. F can represent any of the variables, any alternate AC variable, voltage, current, flux linkage. So, here in the Clark transformation, we transform from 3 phase ABC to stationary alpha beta. So, we have FA, FB, FC 3 phase quantities, and transformed by Clark transformation to F alpha, F beta and FO, 0 sequence component, 3 components. So, this is the Clark transformation. Only thing is, in this transformation our this is the axis A s and this is also the axis of alpha s. Previous transformations we are combining A s axis with beta s. Here we have combined alpha s with A s. Everything is any convention is applicable, and this is the axis of beta s. With this transformation, so angle between so we have f alpha is f a minus half into f b plus f c, and multiplier is root 2 by 3. So, these transformations are obtained by same way by using the component resolution with this convention thing. So, and the inverse Clark transformation from f alpha, f beta and f 0 to f a, f b, f c, just reverse one. So, what is the advantage here in this transformation? So, this is the transformation matrix Ks1, let us say, and this is the inverse transformation matrix. So, Ks1 inverse. What we see for this transformation, Ks1 inverse is Ks1 transpose. The inverse of the transformation matrix is the transpose of the same matrix. Ks1 transpose is the inverse of the matrix. That is the advantage. So, here power remains invariant and only multiplier is different. Only difference is in multiplier, which is root 2 by 3, and it is same in both the transformation matrices. So, that is the advantage of this in power invariant transformation. So, then Park transformation is applicable, same thing. So, between D and Q angle is alpha. So, it is like this, alpha, beta, D, Q. This is rotating at omega e, and this angle is theta e, and this angle is theta e. So, here you have same thing by resolving the components, we get the Park transformation from alpha beta to dq and dq to alpha beta. So, in this power invariant transformation matrix transformation, so the active power P is given by P is V q I q plus V d I d, and reactive power Q is V q I d minus V d I q. This is the active and reactive power expressions in the power invariant transformation. You can see there is no multiplier, like previous transformation we had multipliers 2 by 3 in the transformation matrix. So, but in this case there is no multiplication in P and Q, that you can see. You see V d in D axis winding has a voltage V d and carries current I d. So, power due to D axis winding is V d into I d, voltage into current, because they are DC quantities, and another axis in the quadrature of axis is V q axis winding, it has voltage V q across it and it carries current I q across it. So, power in the q axis winding is V q into I q because it is DC. So, total power is V q I q plus V d I d, and reactive power, because it requires a cross multiplication, D axis current into q axis voltage minus D axis voltage into q axis current. So, this is the active power and reactive power expressions in the MMF invariant transformation. Same thing also, the reactive active power is VDS IDS plus VQS IQS whole into 3 by 2. This 3 by 2 comes because flux is invariant, power is variant, but flux is invariant, because so because in the voltage equations we multiplied a factor 2 by 3. So, that is why 3 by 2 term is coming, and similarly reactive power is 3 by 2 VQS IDS minus VDS IQS. Okay. So, this is all about reference frame transformations. Thank you for attention.